Welcome to Real Civil YouTube channel. In my previous video, which was in detail how to analyze and design G+2 building for gravity loading. So I have covered everything in that video. This video I am going to discuss in detail equivalent static method and response spectrum method with respect to all the codal provisions given in IS 1893-2016. Also, we are going to see the eccentricities, how to model these eccentricities in Etabs. So it will be a very detailed video. So let's begin with equivalent static method. I will go with Etabs software plus with the codal provisions also. So it won't be any software based video, but I will show the detailed clauses from IS code also. Okay. So IS 1893-2016 7.6 equivalent static method is there, and this code has written very well this method. So to create, we have to go to load pattern. Here we have to create earthquake in X direction. Here we will create the positive case. Here you have to select the type seismic and the code IS 1893-2016. Add new load. Similarly, we can create EQY plus load case. Okay. Now we will modify the data. Okay. So first point is direction and eccentricity. For X direction, we'll keep X direction plus eccentricity, X direction minus eccentricity. Okay. Right now we don't have any eccentricities. Okay. After analysis, we will get the eccentricity, and I will show Excel sheet and the calculations as per IS 1893. Okay, so manually it is very difficult and time consuming to calculate the eccentricity. So first we'll analyze, we'll get the data, and then we will put again. Okay, so here seismic coefficient, that is zone factor, site type, importance factor. So in IS 1893-2016, we'll get this seismic zone factor, or basically if you go to page 9, the formula is given Z by 2 SA by G R upon I. So we have to give the input in Etab. Okay, so we have to define, we have to give the zone factor, SA by G, response reduction, and importance factor. So for zone factor, you can refer to table number 3, seismic zone factor 2, 3, 4, 5, or you can see our map of India, or even you can go with Annex E, which is on page number 36 of IS code. Okay, from here you can get the zone factor. It basically depends where your location is. Okay, or if you are confused about the zone, is it zone 3, zone 4, you can check my video. I have shown you how to check the super quality map. So that video is also available in the description box, you can check. So our town is Ajmer, that is zone 2. So here value is 0.1. Site type, For site type, there are basically three conditions for site type which are given. I will show. Yes, rocky or hard soil, medium steep soil, and soft soil. So in our case, it is medium steep soil. So we will select two. Then importance factor. You can get this importance factor on page number 19 of IS code. So here you can see the importance factor. It depends upon basically the type of structure. Okay, so if it is a critical governance building, school, signature building, the importance factor is 1.5, and some other structures are also given. For residential commercial building, it is 1.2, and for all other building it is 1. So in our case, we are considering it as a 1.2. Next, time period. Now this point is very important because we cannot go with program calculated, because if we go with program calculated, you can see our structure, there are beam column slabs. Okay, so there are no any infill walls we have modeled. Okay, so program will not calculate the that stiffness, will not consider the stiffness of that infill wall. So it is better we should go with IS code. We will calculate it and we will put it manually. Okay, so to get the formula of time period, we have to go to page number 23. On page number 23, there is a clause 7.6.2. The approximate fundamental translation natural period TA of oscillation in seconds shall be estimated by the following expressions. So the first option is of bare moment resisting frame, that is without any masonry infill. So it is not for our case. Building with RC structural walls, that means shear walls are there. So again, in our case, there are no any shear wall. So all other buildings is the third case. Okay, so we can go with this formula, 0.09 h upon root d, where h is the height of the building and d is the base dimension of the building at plinth level along the considered direction of earthquake shaking in meter. Okay, so let's calculate for x direction. Okay, the formula is 0.09 into height of the structure. Okay, so our height of the structure is 12 meter, and the base dimension, that means dimension, that is x direction length of the building. So in x direction, I will show, first of all I will put this value here. The base dimension in x direction is 5.5626. It is in square root, so raised to 0.5. So it is 0. Sorry, 4579. Response reduction factor, you can get this factor on page number 22, table number 9, response reduction factor for the building. So it depends upon the type of system we are going to design. So in our case, we are going to design reinforced concrete building with special moment resisting frame, that is SMRF. Means we are going to follow the ductile detailing code. So we can go with R value 5. Here story range. So we have to consider the height from the ground floor or plinth level. Okay, below that we don't consider height of the structure, and to the top it is up to staircase headroom. Okay, eccentricity override we will provide it later once we have the values. Right now we don't have any value of eccentricity because we haven't calculated it manually, and which is very time consuming. By default we will keep the eccentricity ratio for all diaphragm at 0.05. Okay, so click on OK. Similarly we will modify for y direction. I will quickly put these values, which is 1.2 here, user define. I will show how I select the height of the structure. 0.09 into height is 12 meter divided by 11.50. I'll just check this dimension. So go to draw dimension line from this point to, it is 11.57. Okay, so go to again define load pattern. Oh, I think it's not get saved. Yes, I will quickly define this. EQX positive seismic 1893 2016, and then EQY. I'll quickly modify this. This factor was around 0.458. Okay, here 1.2 and 0.09 into 12 meter divided by 11.57 raised to 0.5. So 31 around 0.32 second. Ground floor response reduction factor is 5. Click on OK. Click on OK. Now we have created the load cases. Okay, now we have to define the mass source, which is already existing. We will modify it. So click on specified load pattern, and we have here we are uh, giving information to the Etab related to the seismic weight of the structure. As per IS code, we have to consider full dead load. For live load, there is a clause table 10. If your live load is greater than 3, less than 3, or 3, you have to consider 25%. If it is greater than 3, then you have to consider the 50%. And for the roof, you don't need to consider the live load. Okay, for seismic analysis. So make sure you make the cases live load 3, less than 3 and greater than 3 in your load load patterns. In our building, all the live loads are less than 3, so 0.25. Super dead load factor will be 1. Click on OK, click on OK. Now we have to assign the, or we have to define the diaphragm. So we have to define a rigid diaphragm D1. Click on OK, click on OK. Now we have to assign this. To assign this, first we have to select all the floors, close, go to assign shell diaphragm D1, apply, OK. Now we have assigned the diaphragm. Okay, I will delete this dimension. Okay, so the equivalent static method, all the steps are over. Now we will go with definition of response spectrum, and we'll see the process of response spectrum, and then we will see all the clauses in detail. Okay, so for response spectrum, the first step is to define response spectrum function. So go to define function response spectrum. Here you have to select the code IS 1893-2016, add new function. So I will give the name IS Indian response spectra 1893. Zone value is 2, importance factor is 1.2, soil type is 2, response reduction factor is 5. Okay, so this graph is basically showing us period versus AH. Okay, so based on the period, it will automatically calculate the AH value. Okay, so click on OK, click on OK again. Now our first step is over. We'll go to second step. The second step is very important, which is related to the modal analysis, because response spectrum method is a dynamic analysis. It involves the dynamic analysis at some portion of the dynamic analysis. It is not fully dynamic. So go to load pattern. Here just a minute. Yes, go to load case. Here there is a case model analysis. We have to modify this case. Okay, so keep the name model. Okay, then there are basically two ways, eigen and reads. Okay, so eigen analysis is useful for checking the overall behavior, and it is very good under lateral load. Whereas if you want to consider the vertical ground acceleration, that is also we are going to cover in this video, then reads analysis is more important. So we have to select that reads, or in case of localized machine vibration, reads method gives more accurate results, so you can choose that. Okay, so it is okay with eigen right now. Mass source, which we have already defined. Now come to other parameters. So here you can see 1 2 3 4 5 stories are there, and so 5 into 3, so we have to consider up to 15 modes. Okay, minimum number of mode 1. Okay, So here cutoff frequency, basically you can ignore frequency above particular hertz, that is mostly 33 hertz. Okay, so keep it as it is. Make sure it is here allow auto frequency shifting is on. Okay, so it will ignore the minor results, like it will consider 3.01 and it will ignore 3.012, 3.013 like that. Okay, so this step is also covered. Now we have to go to step number 3. For that we have to create the case, that is response spectrum x direction. Here select response spectrum, then here you have to select acceleration, load name u1 in, that is x direction. Defined function will be Indian response spectrum 1893, which we have defined. Scale factor, keep it as it is. We will change it later once we have the results from equivalent static. Okay, then modal load case. So modal eigen, which we have already defined. For modal combination, if you can go with CQC, and there is another method called SRSS. Absolute method is also there. So I have made a detailed video on this, when to go for CQC, when to go for SRSS. Okay, right now in this case you can select the CQC. Okay, then not necessary to consider the rigid response here, because we are not dealing with frequency greater than 10 hertz. For directional combination type, you can keep SRSS method. Modal damping, it is 5%, it is also correct. Diaphragm eccentricity, here initially you keep 0.05. Later once we have the values, we will put here story, diaphragm and eccentricity. Okay, so right now keep 5% as per the IS code for the basic analysis. Click on OK. Similarly, we will create RSPY. So add copy of this case and give the name RSPY. Remaining things will be same. Instead of U1, it will be U2. Click on OK. Now we'll consider the earthquake in Z direction also. Okay, so for that you can see the clause 6.3.3. My motto is you should get aware of all the things in IS code. Okay, here you can see 6.3, design vertical earthquake effects. Effect due to vertical earthquake shaking shall be considered when any of the following conditions apply. If your structure is located in zone 4 or 5, structure has vertical or plan irregularities, structure is rested on soft soil, bridges, structure has long span, structure has horizontal overhang of structural member or subsystem. So any of this case is present in your analysis, in your structure, then you have to consider the design vertical earthquake effect. Okay, in my case the building is not big, again it is lying in lower seismic zone. So I will consider, because to show you the process, I will show how to make it. Okay, so add new case. Here you have to consider response spectrum in Z direction, that is vertical direction. Select the response spectrum. Okay, here we have to consider the Reed's model analysis, not eigen model analysis, because Reed's analysis is very important, or it is very accurate for vertical earthquake effect. So we'll create here another load case, add a copy of the case here. Model Reeds will be there, select Reeds, keep other options as it is. Here acceleration uz will be there. Then here keep it 90%, because target is 90%. And then here 15 and 1 is okay. Now we can create RSPZ case. Sorry. Response spectrum in Z direction. Response spectrum, acceleration U3, IS1893. So here we have to define our function also, because the function for response spectrum Z is also different. Okay, so go back again. So I will show you that clause. So this is our basic formula. Just a minute. Yes, the design seismic acceleration spectral value AV or vertical motion shall be taken as. So here you can see for vertical, this is Z by 2. We have to consider 2/3. There is R upon I, and this value is nothing but your SA by G value. That is the maximum value. So vertical spectral acceleration does not depend upon the time of the structure. Okay, so this formula is for the building. That's why we are considering this particular case. Okay, so we have to define the response spectra. So go to define functions, response spectrum. Here you have to select IS1893 2000. Sorry, here you have to select user, add new function. Okay, so here Indian response spectra for Z direction 1893. Okay, so here period is, will put the period 0, and the value of, here we have to put the value of AV. Okay, so let's check the formula. So 2 by 3 into, here put the value of Z as 0.1 divided by 2 into 2.5 divided by 5 divided by 1.2. Okay, so two by 3 into 0.1 divided by 2 into 2.5 into 1, sorry, 2 by 3 into 0.1 divided by 2 into 2.5 divided by 5 into, sorry, or I will copy this value into 1.2. So this value is comes out to be 0.02. So we have to define this value here, 0.02, and we'll put for 10 seconds also the same. That means there will be a flat line, means for any time period our value will be 0.02. That is the meaning of vertical earthquake. That value, AV value will be there. Okay, because it does not depend upon the time, we have considered the maximum value of 2.5. So click on OK, click on OK. Now go back to load case, response spectra, Z direction, response spectrum, add acceleration U3, default function. Now it is ISRSZ1893. Here model reads will be there. Okay, and then we'll keep the remaining things as it is, keeping the eccentricity 0.05. Click on OK, click on OK again. Okay, so we have already defined the diaphragm. Now go to analyze, set load cases to run. Now before that you can even create the negative earthquake cases. How to create these cases? Just go to load case. Okay, here EQX positive is case is there, so add a copy of the case, make here negative and this factor as -1. Similarly, add a copy of this case, minus here -1. So in negative direction the load will act. Click on OK, click on OK again. For response spectrum there is no need to create the negative case, because in mode shape we are considering both positive and negative, so there is no need to create these cases. Now come to analyze, set load cases to run. Here make sure you click this option, calculate rigid diaphragm center of rigidity, and click on run now option. Okay, after analysis the first thing that we have to check is the base shear. Okay, so here go to tables, go to analysis result, then go to structure output, and then base reaction. Okay, here we will select the AQX, negative AQX, RSPX, RSPY. Okay, so these cases we have applied. So here 1, 2, 3 is nothing but EQX, then EQX with positive eccentricity, negative eccentricity. Okay, that's why there are multiple cases, but base shear is same. Okay, so as per IS 1893-2016, we have to match the base shear of static method with dynamic method, right? So in dynamic method our base shear is 51.9211, whereas in static it is 92.6977. So we have to scale up the base shear of response spectrum method. So I copy this value, Just a minute. First we'll take this value 92, that is the static base shear. Remove this. Just a minute. 92.6977 divided by the response spectrum fx 51.9211. So this is our answer, or this is the factor. So I will open the notepad. Okay. So this is my factor for x direction. Let's calculate for y direction. So EQY, it is again 92.6977, and response spectrum in y direction it is 53.2493. Okay, so 92.6977 divided by 53.2493. So this is the factor for y direction. Okay, so go to, or we'll change it later. Before that, the second thing that we need to check is the minimum design earthquake horizontal lateral force. So if you go to IS code, in IS code table 7, yes, minimum design earthquake horizontal lateral force for the building. So as our building is lying in seismic zone 2, it should be 0.7%. Okay, so that should be the minimum. If it is less than that, then you have to consider this minimum. Okay, usually it doesn't come that low unless you make any mistake. So let's check. Go to reports, project report. In project report we have to, yes, yes, our seismic zone, seismic weight is 3089.9225, and this is our base shear VB 92.6977. Okay, so we can check how much percent it is. So 92.6977 divided by 3089.9225 into 100. So it is almost 3%, and which is way higher than 0.7%. Okay, so that thing is also okay. Okay, so before importing the value, or we'll go and import the values. So go to define and go to load case response spectrum. Okay, here for x direction response spectrum we have to use this multiplication factor. Okay, multiply by, okay, enter, click on OK. Similarly response spectrum y direction. Now check the value of y direction. Control C, multiplication, value, enter. Click on OK. For response spectrum in Z direction, IS code has given the guideline that we have to select the higher one out of X and Y. As the higher one is of X, so we will select this. Go to modify. Click on OK. Click on OK. Click on OK. We will again run. We will wait for the results. So go to tables, structure output, base reaction. Here we will select the case. Now you can see the response spectrum base shear is matched with equivalent static base shear. Similarly, response spectrum in Y direction is matched with with the base shear of EQY. Okay, so that is the first thing. So this is the base shear in X direction. This is the base shear in Y direction. Similarly, these are the results of movements. Okay. Now the second very important task that we have to import the eccentricity. Okay. So there is the codal provision 7.8.2. Yes, design eccentricity. The code has given us the formula. Okay. So design eccentricity will be higher of 1.5 ESI plus 0.05 BI or ESI minus 0.05 BI, whichever is greater, okay, whichever is higher, where ESI is the static eccentricity at the floor, that is the distance between center of mass and center of resistance, and BI is the floor plane dimension of floor I perpendicular to the direction of the force. Okay, so I will show you in the Excel sheet. Okay, so these are our stories: staircase, terrace, shear, second floor, first floor, ground floor. Okay, so this is the design eccentricity for X direction, and this is the design eccentricity for Y direction. Okay, so we have to get the center of mass value. Okay, to get the center of mass value, we have to go to table, structure output, other output, center of mass and rigidity, show table. Okay, now here you can see these are our center of mass values. Copy this in our spreadsheet, center of mass. Then this is the center of mass Y direction. Copy this, paste it. Now center of rigidity in X direction. Now center of rigidity in Y direction. Okay. Now it has calculated ESI, which is this column minus this column, that means 4.45 minus 3.9737, so it will be this value. Now we have to put the building plan length. For X we have to put Y direction, and for Y we have to put building plan in X direction. Okay, so for that we have to go to Etab. In Etab, okay, we have to measure the Y direction. So Right now we are at this, we have to go to staircase headroom. Okay, now y direction. So go to draw dimension line. So y direction is 3.6. So it is 3.6. Then go to this floor, draw dimension line from this point to this point. Okay, it is 11.57. So it is same for other. Okay, this is how we have get the values for this, and we have to consider the maximum one. Similarly, we have to see design eccentricity y direction. Here we have to put the x direction. So draw dimension lines. This is 2.3 for the staircase headroom, and for remaining floors it is 5.6. Okay, this is how you will get these maximum values, and we have to give the input. Okay, so I will delete these lines. Okay, go to load pattern, load cases. Okay, go to load pattern, EQX, modify lateral load. Okay, we have to basically unlock the model. Let me check if I can. Yes, I'll delete these lines. Why I'm not able to select it? I don't know why this dimension line. Yes, okay. Okay, let's go to define load pattern, EQX, modify lateral load. So here we have to give the override of eccentricities. Okay, so ground floor plinth level, D1 is our diaphragm, and this is our eccentricity. Sorry, for ground floor plinth beam, this is the value. Add, copy, first floor D1 is the value, add, copy this value to the second floor, paste this value, add, copy this, erase, paste, add, staircase headroom, copy, add. Click on OK. Click on OK. Similarly, go to EQY, modify lateral load, overrides ground floor plinth beam. This is the values for Y. Copy this, D1, copy first floor. Okay, value can't be negative. Add, copy second floor, add, copy terrace, add, copy staircase headroom, add, okay, okay, okay. Now go to response spectrum case, modify show. Here again we have to, here we will cut this. Here ground floor, first floor, second floor, terrace, staircase headroom, eccentricities, yes, copy, paste, copy, paste, copy, paste, copy, here paste staircase headroom, copy this value, paste this value, okay. And this is for response spectrum in x direction. Click on ok, click on ok. Similarly, response spectrum in y direction, here you have to modify this, here make it 0. Similarly, we will add these stories. So first story will be ground floor, second story will be first floor, then second floor, terrace and staircase headroom. Now we have to copy the y direction values. Ground floor, here copy this value, then again copy, then again copy this value here, copy, again copy and paste. Click on ok, click on ok, click on ok again, okay. Now we have to analyze it. We have entered the eccentricities manually. Now again we will analyze and run analyze. So for semi-rigid, you won't get these values of diaphragm, okay. For that you need to select the rigid diaphragm, and then only we can get these values, okay. Now here you can check the results, okay. You can check the model analysis results post. Here analysis results, you have to go to structure output. In structure output you have to go model information and then model participation and mass ratios. So here you can see the x direction model participation mass ratio in the global x direction, global y direction, okay, z direction, summation, okay. Make sure your summation is 90%. This is the clause, okay. Here we are getting 89.07. So one or two more modes needs to be added here, okay. So we'll do that quickly. Go to define load cases, model load case, modify. So here instead of 15 we'll put 18 modes. Click on ok. Similarly for reads also, instead of 15 we will put 18 modes. Click on ok, click on ok, click on ok, and then analyze it. and run analyze. So this is one codal provision that model 90% mass should be excited. So go to analysis result, structure output, model information, right click, show table. Now here you can see 90% is achieved in the 17th mode. Okay, for x direction, for y direction it's been achieved in 13th mode. Okay, so that clause is also clear. Also you have to make sure that your first two modes are translational mode. So here first mode is uh, y directional dominant. Okay, so 76%. And then your second is ux, that is 40% around. Mass is getting excited 41%. So this is how you can check the results from the model analysis. Then you can check the results for structure output. Here base reaction we have already seen. Okay, for different cases. You can see the change in the movements, mx, my, mz. So movements are there. So due to eccentricity, there will be additional torsion will be there. That means more torsional forces will be there. You can check the joint displacements in joint output. You can see joint displacement, diaphragm center of mass displacement. So you can see the how your diaphragm is moving. Then you can see the element forces for a particular column, the values of torsion, for different cases. Here you can check the floor wise base reactions. So story forces, you can see the story forces. You can check the response spectrum case, AQX case. So here you can see the torsion values. You can see at the top only. EQX and response spectrum values. So this is how you can check the variety of results. You can check any column, and I have shown you can check V2, M3 and torsion. So this is how you can check the results. So this is the overall procedure. I hope this video and the content that I have delivered is useful for you. Thank you. Please like, share, subscribe the channel. Thank you so much.